Okay, lesson 3.8, we're dealing with related rates, and we're going to be looking at measurements that are changing with respect to time. And no doubt about it, the two asterisks at the top, please copy that down. When a quantity is increasing, that is, it's getting larger, the related rate that would describe that quantity is known to be positive. By way of comparison, if a quantity is getting smaller, if it is decreasing, then the related rate is negative. And it's always a rate with respect to time. So as I'd mentioned earlier, all of these problems, guys, are going to have a different setup. You're going to really go back to all experiences that you had in mathematics. A lot of geometry. Lots of geometry can be applicable. Trig will also show up. So you're going to model a real-world scenario with geometry, trig, or just in a general equation, and then take derivatives with respect to time to see what's occurring. Let's take a look at such a problem. Example 1, it says a ladder that's 10 feet long. And by the way, do you think that is changing? No way. This is always 10 feet. And that's another challenge as you're working through these problems. Sometimes, given information, you're going to have to realize that's not changing, that's not varying, it's not a variable. This is fixed at 10. So you've got a 10-foot ladder, it's resting against a vertical wall. Well, my goodness, is there any other type of wall, I guess we could ask. But regardless, we could say if the bottom of the ladder slides away from the wall. Now you can envision what's happening. That ladder is moving away. As that ladder would be moving away, just a moment later, it might be way out over here. What's happening to that distance from the foot of the ladder to the wall? It's getting bigger. Do you see that? As that ladder, as it slid down, look at this lighter sketch that I just made. Do you see how x would get bigger? So if you're going to have this ladder sliding down, its height, the distance from the ground, is decreasing, isn't it? And it's only going to be certain values for a split second. You see, x and y are changing. By the way, x and y, and this is so important, are functions of time. That's what a lot of calculus textbooks kind of drop the ball with. I really think if we spell that out, that's going to help kids understand what's happening. In fact, all that you're doing today in general would be considered functions of time. Now, at first, that might not seem to be very pertinent. It truly is. But look, we've got this setup, and they're saying, how fast is the top of the ladder sliding down when the bottom of the ladder is 6 feet from the wall? So this is the question that we'd like to answer, of course. How fast is the top of the ladder sliding down? That's a rate. We're supposed to find a rate. We're supposed to find dy dt. How fast the top of the ladder is sliding down. How is y changing with respect to time? When the bottom of the ladder is 6 feet from the wall. So we want that at a particular instant. When the ladder is 6 feet from the wall, when what variable would equal 6 clearly? X. Now, would x always equal 6 for this problem? If so, you couldn't slide down, could you? Right? So, I guess that's the first thing. You have to understand the 10 is fixed. It's always going to be 10. But x and y are changing. Here's where it's so critical and so important. You have to model this situation. And you go back to your tool belt. You go back to geometry. You go back to trig. You'd say, can I come up with an equation that relates x, y, and 10? And the answer, I hope, is yes, meaning how? What would relate x, y, and 10? The most famous geometry theorem of all, the Pythagorean theorem. You know it. So I'm going to say 10 squared equals x squared plus y squared. And usually kids look at that and they'll say, sure, that's fine. And then we, are going to take derivatives. We can take derivatives now. What's the derivative of 10 squared? 0. It's a constant. What's the derivative of x squared? 2x dx dt. And right now I want to say something. If you were to look at a college campus right now, if you saw the professor writing that up, and if you could have the camera zoom in on the audience, you'd see all these kids begin to make some funny faces, right? And I think you can sympathize with them, can't you? You'd say, well, wow, just yesterday I took the derivative of x squared, I got 2x. And now you're saying, oh yeah, it's 2x dx dt. Yeah, and then we're going to keep going, and like over here, you take this derivative, it's 2y dy dt, and kids are frantically copying down their notes, and they're saying, wow, I don't know about this. And that starts the confusion with related rates. All of a sudden, kids are like, I don't like this. This isn't what we were doing a couple days ago. Now all of a sudden, dx dt's are popping in all over the place. I don't get it. Well, here's where authors have kind of dropped the ball a little bit. X is a function of time. Y is a function of time. You want to know what x is, you plug in a certain t value. I don't know what that function actually looks like. I'm just calling it x. But do you know what? When I'm looking at it this way, I've got x of t quantity squared. Here's y of t quantity squared. And now when you take the derivative, you'd have to do the same basic concept we've been doing the last couple lessons. We'd have to do the chain rule. Where's that dx dt coming from? From the inside. It's a function of time on the inside. That's where that's really coming from. Now, I don't have to tell you, you look in your book, and you won't see them write that there. They might say, oh yeah, it's a function of time, and kids will get it. But if we don't spell that out, more than a few kids are going to say, well, I guess sometimes you throw in a dx dt, sometimes you don't. I have no idea when to do it, but professor says to do it, so I'm going to do it now. I don't know why I didn't do it a couple of days ago. Right? But so are we feeling okay just up to here right now? Okay, so here's what's happening. They're saying, how fast is the top of the ladder sliding down? They're saying, find that rate of change with respect to time when the bottom of the ladder is 6 feet from the wall. Well, that's only for the briefest moment. For just the tiniest split second. You see a ladder sliding down the wall, hey, there's a lot going on. That's happening fast. And next thing you know, you hear the crash and the ladder hit the ground. But just for the briefest split second, that ladder was 6 feet from the wall. When it was, what's y going to equal? Y is going to equal 8, isn't it? Why? Because it's a 3, 4, 5 family. Or you could do the Pythagorean theorem, right? So you can use the Pythagorean theorem. So y is equal to 8, x is equal to 6 at that brief second. And here's the other thing that, forgive me, as I was hastily writing this all out, I didn't call attention to, if the bottom of the ladder slides away at a rate of 1 foot per second. Wow, that's a rate too, isn't it? That's a rate too. So if the bottom of the ladder is sliding away, the bottom of the ladder is down here with x, isn't it? dx dt, is it getting bigger or is it getting smaller? It's getting bigger. Oh, it's a positive 1 foot per second. That's what you always have to pay attention to. Am I getting bigger or am I getting smaller? And from here, guys, as we go ahead and just finish this up, we can say, well, my goodness, look at this. X is equal to 6. dx dt we just found is 1. We read that in the problem. For the briefest moment, y is 8 feet. And then we can find dy dt. By the way, you could have divided both sides by 2 if you wanted to earlier. That would have been very clever. But look, regardless of whether you do or don't, here's your 12 plus 16 dy dt. And tell you what, how about we just go ahead and subtract a 12. And then we divide. And 12 divided by 16, well, you get the idea. We could divide out, a 4, I guess, right? And what do we get? Negative 3/4. Hey, we knew already the height was shrinking. My rate of change should be negative. It's negative 3/4 feet per second. And guys, that's how you do a related rate problem. Your quantities are functions of time. You have to pay attention as to whether those quantities are getting bigger, increasing, or getting smaller, meaning they're decreasing. That affects the sign, S-I-G-N, of your related rate. We doing okay? All right, let's put an end to this thing right here.